In this lesson, we will examine two more common myths about data sufficiency questions. The first myth is that one equation with two variables never provides sufficient information in a data sufficiency question. Now granted, there are some cases where this rule does apply. The problem is that it does not always apply. Here's an example where the rule does work. In this question, we want to find the value of x. Statement 1 tells us that 2x plus 3y equals 11. Here we have one equation with two variables, and in this particular case, the statement is not sufficient. The statement is not sufficient because there is an infinite number of solutions to the equation. Here are just a few of them. Since this equation has an infinite number of solutions, there is no way to determine the value of x with any certainty. So in this case, one equation with two variables did not provide sufficient information to answer the target question. Now these results are sometimes expanded into the myth that suggests that one equation with two variables never provides sufficient information. This is not the case. Take this example. Here we want to find the value of x, and statement 1 gives us one equation with two variables. Before we conclude that statement 1 is not sufficient, let's take a closer look at this equation. We can simplify this equation by first expanding the right-hand side, and then simplifying the right-hand side. From here we can subtract 2x from both sides, and now we'll subtract 5y from both sides. Finally, when we subtract 2 from both sides, we can see that x equals -4, which means statement 1 is sufficient. Now it could be argued that this equation does not really have two variables, since one of the variables essentially disappeared upon closer inspection. The point here is that some equations may look like they have two variables, in which case we may draw the wrong conclusion about whether or not they can be solved, so watch out for that. Here's another question with one equation and two variables. Here we want to find the value of x, and statement 1 gives us one equation with two variables. Before we conclude that statement 1 is not sufficient, let's take a closer look at this equation. First, we'll factor the left-hand side, and now we'll divide both sides by 5. When we do this, we get 2x plus y equals 3. Now, under most circumstances, there would be an infinite number of solutions to this equation. However, we need to remember that the question tells us that x and y are positive integers. If x and y must be positive integers, then there is only one solution to this equation. It must be the case that x and y both equal 1. So statement 1 is sufficient. In this case, the condition that x and y are positive integers made this statement sufficient. Keep in mind that although I am presenting these examples as equations, the same situations can arise through word problems where you must create the equations from the information provided. Now when it comes to word problems involving real-world situations, be extra careful to note those situations where it is implied that the variables are indeed positive integers. Now here's one last example involving one equation with two variables. In this question, we want to find the sum of x and y, so this already makes this question different from other questions. The potential mistake here would be to conclude that in order to answer the target question, we must find the individual values of x and y. Now, if we were required to find the individual values for x and y, then statement 1 would not be sufficient. However, we are not required to find the individual values for x and y, we are required to find their sum. So if we take our equation and subtract x from both sides and add y to both sides, we get 4x plus 4y equals 12. Now, if we divide both sides by 4, we get x plus y equals 3. So the sum of x and y is 3, so it must be the case that statement 1 is sufficient. The next myth to discuss is the one that says two equations with two variables will always provide sufficient information to determine the individual values of x and y. Now sometimes this rule works. For example, in this question, we want to find the value of x. We are given one equation with two variables, and statement 1 provides a second equation with two variables. Do we now have enough information to answer the target question? Yes, with these two equations, we can use one of several methods to solve for x and for y. So in this case, having two equations with two variables provides sufficient information to determine the individual values of x and y. However, this is not always the case. Consider this example. Here we are given one equation with two variables, and statement 1 provides a second equation with two variables. Do we now have enough information to answer the target question? The answer is no, and here's why. If we take the equation from statement 1 and first rearrange the terms, and then divide both sides by 2, we see that our second equation is identical to the equation we were given. So while we may indeed have two equations with two variables, the two equations are essentially identical. As such, we cannot solve for x and y, in which case statement 1 is not sufficient. So be sure to watch out for situations where there are two equations with two variables, but the two equations are essentially identical to one another. Now here's another example where the myth fails. In this question, we want to find the value of x. We are given one equation with two variables, and statement 1 provides a second equation with two variables. In this case, the two equations both have two variables, and they are not identical. However, when we combine them, we still do not have enough information to solve for x and for y. Let's see why. First, we'll take the equation x plus y equals 7 and solve it for y to get y equals 7 minus x. Then we'll take the y in the second equation and replace it with 7 minus x. We now have an equation we can solve for x. From here, we'll expand the left-hand side. And now, since we have a quadratic equation, we'll set the equation equal to 0, at which point we'll now factor the right-hand side. From here, we can see that x equals 3 or 4. Since we have two possible values for x, statement 1 is not sufficient. So what is the problem here? The problem is that these two equations are not both linear equations. A linear equation is one that can be written in the form ax plus by equals c for some values of a, b, and c. And if we have two different linear equations, we can solve them for the two variables. Now the given equation is a linear equation, but the equation in statement 1 is not a linear equation. So the two equations combined are not sufficient to solve for x and y. To summarize, in this lesson we examined two common myths. The first myth is that one equation with two variables never provides sufficient information in a data sufficiency question. The second myth says that having two equations with two variables will always provide sufficient information to determine the individual values of x and y. While both of these myths can apply to several situations, they do not always apply. So watch out for the traps we looked at in this lesson.